Hi there, my name is György Krajcovic, but everybody calls me Cryo for obvious reasons. And I work as a software engineer at Grafana Labs. I work on Mimir and currently mainly on native histogram support. And I see people filtering in, so I'll say a few words about native histograms first, which is not the topic here. But everybody talked about native histograms, so I feel like I should mention it that Mimir also supports native histograms ingestion, both through Prometheus Remote Write and OTLP, so you can send exponential histograms as well. And you can try it out with Mimir. In Grafana Cloud, it's still in preview, so you need to send a support ticket, but we can enable it and you can try it out. But that's not the topic. I will talk about yet another streaming Prometheus engine. First, a few disclaimers. Actually, this work is very, very experimental. It was done by one person during a week-long hackathon at Grafana Labs. And actually, that person wasn't me. So it was done by Charles Korn, but unfortunately, he couldn't make the conference. So if there are some mistakes, then it's probably me explaining it wrong. All right. So let's get into the problem that we are trying to solve. So I'm going to talk about this problem in the context of Mimir. Mimir, for the purposes of this talk, is a scalable microservices architecture time series database built on Prometheus. It provides Prometheus API compatibility. And it's great at ingesting huge amounts of time series. We demonstrated that you can ingest 1 billion, that's a billion with a B, time series in a single cluster of Mimir. However, it could be a little bit better at acquiring huge amounts of data. And in particular, we'll look at a component called Queryr, which is the bit that actually houses the PromQL engine. And this is a graph of the memory consumption versus time of our queryers. This is from an actual production cluster. And you can see that there's kind of a steady state, but there are like peaks of double the memory use of the steady state. And this is kind of an issue because we are paying for the memory that the maximum memory that we use, so basically we are paying for the peaks, but we are actually not using that much memory all the time. So that's kind of wasted. And the worst part is that memory isn't really elastic. So when you go over the memory limits, your pod will be killed, and in the best case, the user will notice that the query runs slower because we will retry. But in the worst case, it will just not work, and you get to 500. So that's not ideal. So the question is, why does this happen? And let's look at a very simple query example where this comes up. Let's suppose that you're running the sum over some metric selector as a range query. What happens in the PromQL engine, in the vanilla engine, is that the engine will load all the samples from the metric selector, and then in the next step, it will calculate the sum. And basically, the first operation, this loading of all the samples, is the part where we run into this issue that we can load so much data. Remember, Mimir is distributed and scalable database, so we can load huge amounts of data. This is where we can run out of memory. Actually, this isn't a new problem. So we already know about this, and Mimir has some strategies to mitigate it. First of all, if we are looking at this query over 5 days, so the range is 5 days, our first technique is that we are going to split up the query onto days. So we will run some metrics on the first day, second day, first day, and we can distribute this over many queryers so that we are not using the memory in one place. The second technique is actually query sharding, where we are taking advantage of basically the properties of sum, that you can create a sum from the parts of the sum of the parts, and we are sharding a series and then creating sums and sum them up. And the third thing that we do is that when we are loading series into memory, we do something called chunk streaming, where we are not loading all the chunks, the underlying physical storage of samples all at once, but we are loading them in the stream. And this chunk streaming actually enables us to reduce memory utilization in queries to around 20–30% in some cases. And then the final line of defense is limits. This is the bit that nobody really likes. We have to configure them, and then when users run into them, they might get some really cryptic error messages, like chunks limit reached. So this is not ideal. We'd prefer to just actually do the query and not run into these limits. In summary, we are doing a lot already to mitigate the effect of loading too many series, but we could do even more. And at this point, some of you might be asking yourself, so what about the Phanos' streaming engine? Last year, Philip and Bartek demoed Phanos' new PromQL engine, which computes results by streaming results by time step. So basically, they are streaming by time, and it uses parallel programming to achieve impressive query latency. And indeed, we did run tests and try this out. We did some experience. And it turns out that, unfortunately, for our use case, in itself, it's not quite the right fit. And I will explain the next slide why. So there are a few main reasons why this is. First is that, according to our statistics, something like 90% of the queries that we see in production are actually instant queries, where there's no real time steps. Think about alerts, recording those, summary numbers on dashboards, etc. And then a big benefit of the streaming by time step is splitting up by time, but we already do that. So if we are looking at long-range queries in multiple days, we already have the splitting by day, so the time splitting. On the other hand, on the flip side, what we do see is sometimes queries loading huge number of series in one step, in one time. And so think about monitoring Kubernetes. If you have a large Kubernetes cluster, your time series could number in hundreds of thousands or millions even. And so in this case, streaming by time series doesn't help us too much, because even in one point in time, we can load a huge number of series. So if we could combine this splitting by time, splitting by days, and then streaming by series, then that would basically put a cap on how many series we load at the same time, and put a cap on how much memory we use. So to summarize, streaming by time step isn't quite right for us, but we do believe that streaming is the future. And here, but just a different kind of streaming, streaming by series rather than by time. So going back to the example from before, the sum. So this is exactly the same sum as from before, but this time we are going to do a different strategy. So this time we will load the first time series and then add it to a running sum. And then load the next time series, add it to the running sum, and so on until we loaded all the series and created the sum. And this strategy can work even if the the expression is more complex. We can make this recursive, so basically stream the result of the sum as a series into the next operation. Also, it can work if you have a group by, so you say something like sum by cluster or sum by node. We just have to make sure that when we are creating the running sum, we know which series goes into which group. And then once we collected all the series for a group, then we can emit that sum for that group. Yeah. So why do we think this is better for Mimir? It all comes back to peak memory utilization, right? This kind of strategy aligns well with what we already employ, which is streaming by chunks of series, and then which means that we don't need to load all the chunks for all series into memory. Also, the peak memory utilization of such strategy is determined by the cardinality of the output. So basically, in this case, the coordinate is 1, we just get one sum. If there's a group by, then the cardinality is how many groups you have, and that's going to be directly proportional to how much memory you use because of the running sum. And furthermore, because we are doing these things over and over, like load the series, add it to the sum, load the series, add it to the sum, we can reuse that memory and kind of take away some pressure from the garbage collector. So this is basically exactly what Charles has prototyped, and meaning that he wrote basically a full replacement of the PromQL engine, but obviously he didn't implement everything. He just implemented the metric selection, the loading, sum, and rate. But it was enough to run some measurements already. So let's look at some measurements. I know that people tend to always look at the colorful bits, so I'll explain that first. So the measurement was done like this. You take Mimir, and it already has the Prometheus engine, but you can switch it out with this new engine that Charles wrote. And also you can swap it out for the Phanos time slicing, time step streaming engine as well. So that's what the measurements are. The red one is with the Prometheus engine, the orange one, the middle one is with Charles's prototype engine, and then the blue one is as Phanos. And on the left side, you'll see the peak memory utilization, and on the right side is the P95 latency. So the measurements were run on a few different use cases. Actually, this use case is the kind of the worst one for this, almost the worst one for this engine. This is when you're just straight up loading a bunch of series. In this case, we're loading 1,000 series over 1 hour range, 15-second step. This isn't terribly useful because, like, how are you going to show it in Grafana, for example? But still, it's a good measurement point. So here you can see that actually the memory utilization is worse than both Prometheus and Phanos, and also the latency is worse. And that's because, well, A, it's an experimental thing, then B, it does introduce some overhead into the processing. But having said that, this is experimental, so it could be optimized. And actually, in the worst case, we could default back to the original engine if we cannot optimize it further. So it could be on par with the Prometheus engine. So let's look at a better case. This is including sum and the sum going into some few groups. So this is 100,000 series into 10 groups. And here we start to see the benefits of streaming. The memory utilization is like 1/10 on the others. And on the latency side, it's still a bit slower than the others, and especially Phanos. We think there's some way to improve on the latency, but remember, our main concern at this point is memory, actually. So let's look at another. Yeah, and just to drive home this idea of the memory utilization depending on the output, basically the cardinality of the output, here's a graph of memory utilization on the y-axis versus the number of series that you put in. And you can see that basically the streaming by series engine flattens out quite soon and stays there because we are not loading all the series, we are just loading what we're actually adding to these groups. All right. Here's another example. This is an instant query now, so this is not a range. This is 100,000 series 10 groups. And actually, this is very important for us. Like I said, 90% of the queries that we get are instant queries. And here, the memory utilization is night and day. So streaming by series has like 35% memory utilization, less memory utilization, and less latency. So this is where you can see that streaming by time step doesn't have that much because there's basically just one time that we're evaluating for. And let's look at the scenario where we would expect the streaming by time step to shine. This is a long-range query. This is 12 hours now, not 1 hour. But we had to reduce the number of series because actually on a laptop, it was too much, like 100K series for 12 hours. Here we see that the streaming by series and by time step performs similarly, but the streaming by series is still a little bit faster and uses less memory. And however, well, all is not like great. This is again experimental, and there are some cases that trip this up. So if you look at a query like this, it's kind of a join on Node, and if you look at how Prometheus will break this down, we'll get the one sum on one part of the division and the other sum on the other division. And the problem is that when we are streaming the results from these two sums, there's no guarantee on the order of the result, like what's the order going to be. Meaning that basically at the division, we have to wait and buffer the partial result until we get the corresponding result from the other side. But note that even in the worst case, this is just going to use the same amount of memory as before. But if we are lucky, then it will reduce the memory used because we will do those matches earlier. Yep. So what's next? This is still an experiment, and the results are looking pretty great, like very encouraging, but there's plenty more work to be done. And we are going to continue investigating this, expanding the engine's capabilities, and this is something that we want to pursue further for sure, because it's addressing a real problem that we have with memory utilization. And you can check out the code. It's in a branch in Mimir, and also there we have a blog post about the 1 billion series that I mentioned, and that's it. Thank you very much.
Hey, thanks a lot, Kayo. Really amazing. So I'm looking forward to seeing more of that in the future.
Thank you.
Any questions, anyone? Raise your arms. I don't see anyone. Any questions? Come on. Yes.
Yeah, thank you. Did you try like a hybrid approach where you do like parallelize some, like one by one, and then gather the results for your time series?
You mean parallelize?
I mean, like for the sum, like you take one time series and you sum it. You take a new one and you sum it. Do you do that in parallel or do you do that in one worker?
It's done in kind of two passes. I didn't want to go into too much detail here, but what happens is that we load the series, the names of the series basically, group them, and then we run in a second pass the, we go through each series and add it to the sum of the group that it belongs to. It's not in parallel. I guess we could do something in parallel, but like that's something to do next.
Any more questions?
Okay, then I'll have one. Did you attempt to work with the Thanos project on this?
I think, I'm not sure if there was a connection. We haven't talked about that with Charles. I assume that there was some interaction, but I'm not sure.
Okay.
Obviously, we are not opposed to it. Like I said, it's a work in progress. It would be great to combine all things and.
Right. My thought also was like in a lot of query optimizers and stuff like that. This would have like a cost optimizer for the query, right? And it would decide this particular strategy is actually better for this query, and maybe for other queries this other approach is better.
Yeah, definitely.
Well, I think like he can answer my question. It was related to it. Like, can you choose or different query engines based on the query? Like, if it's an instant query, you would use this one. But then if it has a lot of timestamps, you would go with the Thanos one. Like, I don't know. Are there any plans to do something like that?
Yeah, we want to, explore our possibilities basically at this point. So that's definitely one idea. I think another idea that came up was optimizing like how we get, in what order we get the series, and maybe do something like to optimize for the join cases, but it's early days, but definitely in the cards, yeah.
Hey, fantastic presentation. Would you have benchmarks for longer time queries and how this compares to, for example, Thanos engine? So you showed like 12 hours.
Yeah.
Would you have something for like 30 days and like a breakdown where streaming actually breaks down and increases latency, for example? Would you know this?
We haven't run those because, like I said, it was run on a laptop. But definitely, we want to do more tests with like bigger data sets. But again, in Mimir, we already are breaking down those long-running ranges into days. So basically, it makes sense for us to concentrate on below 24 hours, because over 24 hours, we are already splitting up.
I see. Thank you very much.
Sure.
So, any more? We can take one last question if there is any. Yes.
Yeah, thank you for the talk. Just one question. Are there any plans to introduce downsampling, like it's already available in Thanos, to reduce the number of samples to load in the first place?
What was the question, sorry?
If there are any plans to introduce downsampling in Mimir.
Oh, sampling?
Downsampling of the metrics, like it's already available in Thanos, like to reduce the number of samples.
Okay, that's a very good question, but I don't know the answer to that. Our current strategy is that you can use adaptive metrics to reduce your, cardinality of your metrics. Obviously, we are looking at all possibilities, and we have been looking at downsampling and something like that, but it's not like I cannot say anything about like roadmap or promise anything.
Cool. So thanks again. It was very interesting. And we have now 5 minutes for switching the speaker. And the next talk is on configuring the OpenTelemetry collector for Prometheus. Thanks.
Thank you.